Okay, the fission of a large nucleus like uranium-235 can be induced by firing a slow neutron array. These slow neutrons are sometimes called thermal neutrons, and they're slow enough that they get absorbed by the nucleus, and this makes it unstable. So in this case, it becomes uranium-236, which splits into two roughly equally sized daughter nuclei, and these daughter nuclei, they're radioactive and they can emit alpha and beta and gamma. Okay, also these daughter nuclei have a higher binding energy, so it means that some energy is released, and this mainly goes into neutrons that are also released in this process. So these fast neutrons can go on to do fission. So the fast neutrons that are released, they need to be slowed down first before they can be absorbed by another uranium-235. So this is done by moderator particles like this. For example, water and graphite. The fast neutron collides with these and it loses its energy, some of its kinetic energy, and slow enough that it can be absorbed by the uranium-235 and cause another fission reaction. And so the function of the moderator, the neutrons collide with the moderator particles and lose kinetic energy, slowing down, and they become thermal neutrons which can be absorbed by uranium-235. And this can continue, okay, and this is what a chain reaction is. Okay, so we can see that, for example, one reaction can lead to 3 neutrons, and that will lead to 9 and then 27, and by the time you've gone to like 20 sets of reaction, 3 to the power of 20, that's more than a billion reactions. So these reactions can go out of hand very quickly, and a lot of energy can be released in a short period of time. Okay, we're going to look at how nuclear fission reactors are used to generate energy. So firstly, we've got a concrete shield, and this absorbs any gamma photons or any neutrons that are produced from the reactor core. Okay, the reactor core and the heat exchanger are made out of steel that absorbs any alpha or beta and some gamma that's produced. Then inside that, we've got the fuel rods. Now the main ingredient in the fuel rods is uranium-235, sometimes plutonium. And there are uranium-238 inside the fuel rod, but however these don't undergo nuclear fission. The uranium-235, it needs to be enriched, and that needs to up to a critical mass. So there needs to be at least a minimum amount of uranium-235 for a chain reaction to start. Okay, so if there isn't enough, the neutrons will just escape without being absorbed. Okay. Okay, next, inside the reactor core, we've got moderators. So for example, water or graphite. The neutrons collide with these moderators. They slow down, they can be absorbed by the uranium-235. And then we've got coolants. Coolants also absorb the energy by collision with the neutrons or from the radioactive daughter nuclei that are produced, absorb the energy from them. And they transfer this energy to the heat exchanger, where it can be transferred to a turbine, and this can spin the turbine and generate electricity, for example. So coolant, for example, we use water, or in a gas nuclear reactor, we use carbon dioxide. Next, the most important part here is the control rods. Okay, so control rods absorb any excess neutrons inside the reactor, so that only one fission reaction leads to one further fission reaction, so the chain reaction doesn't go out of control. So if you wanted to stop the chain reaction or decrease the rate of the nuclear fission reaction, you can lower the control rods in like this. Okay, the control rods are made out of boron, and this absorbs these extra neutrons, and it can control the chain reaction.